Hey everyone, my name is Connor. I'm a fourth year here at Queens, and I'll be a project manager this upcoming year on QMind. So today I'll be doing a presentation on unsupervised learning. So what is unsupervised learning? Earlier today, a lot of you probably would have seen the presentation on supervised learning. And the biggest difference between unsupervised learning and supervised learning is that unsupervised learning doesn't have labels for the training data. So that means instead of training our model so that it makes the correct predictions, instead we're searching for patterns within the data. So the typical types of applications that we'll see with unsupervised learning are used to either gain insights into the distribution of data, as well as also pre-processing for later use with other algorithms. So a major part of unsupervised learning is clustering. And essentially a cluster is just either a related group of objects or looking at dissimilar groups of objects, so seeing the differences between clusters. And what we're looking for is essentially very tight-knit groups, so high inter-class similarity and low inter-class similarity. So what that means is we want well-defined groups where the individual objects within the groups are very tight, but then lots of separation between the different groups. And typically we're able to measure that using a similarity measure. And also that will help hopefully discover hidden patterns that we wouldn't necessarily be able to see without using these algorithms. So in order to measure the quality of our clusters, we use typically a distance function. And distance functions can vary depending on the type of data. So for example, if you have Boolean data, it's going to look a lot different than if you have categorical data or even like text. However, some of the more commonly used distance functions would include the Euclidean distance or the Manhattan distance. And there's also different approaches for clustering. We won't dive into all of them, and we'll just take a quick look at k-means. But the four kind of different buckets that you'll typically see are partitioning, hierarchical, density-based, and grid-based approaches. So I'll run you quickly through a k-means clustering algorithm to hopefully give you kind of a visualization of what's going on and how to implement it. So the first thing you're going to want to do is pick the number of clusters, or k. And then you're going to want to set the randomly a centroid for each cluster. And that essentially means the center point for each cluster. And then within that data, what you're going to do is every data point closest or closer to, or you're going to assign it to the closest center point for the cluster. So in the example here, you'll see that this green line will divide the data points. Anything above the green line will be associated with the blue cluster, and anything below it will be associated with the red cluster. And so what we do is we assign each point to the associated cluster. And so you can see here where each of the data points turns blue or red. And then after that, we're going to then move that center point to the center of all the data that's been assigned. So you can see here the blue and the red squares are moving more towards the center of their respective clusters. Once that happens, we're going to then split up the data again. So as you can see, now that these two squares have moved, there's three data points that have kind of crisscrossed. So the one red point above the line will now become blue, and the two blue points below the line will become red. And so we keep doing this and we iterate through this until we get to kind of a convergence and when our center of our clusters no longer move. So we're going to see that it's just going to keep slowly converging. It'll typically, you'll see smaller and smaller steps until you've reached a final point. So here, in this instance, our center points would no longer be moving, and then we can say that the clustering is finished. And with that, since we've picked two clusters to begin with, we'll end with two kind of distinct groups, and hopefully you'll see that the groups are as tight as possible and also having more space between the other clusters. So a few things to be aware of when implementing k-means clustering is that it'll often converge to a local optimum. Because once it stops moving, the algorithm is done, it won't necessarily get further away in order to reach the maximum optimum. Another important consideration is you need to specify the number of clusters. And this can be sometimes a little bit tricky. But in other instances, it can also be quite intuitive depending on the problem at hand. Another consideration is that it's really sensitive to noisy data. So if we go back to one of these examples, let's say we had a point that was like way to the like up and right, that's going to pull the blue cluster away, and then you'll probably see changes in data because of that one noisy point. And then the last kind of big consideration that I want to highlight is that it isn't conducive to finding non-convex shapes, and this is kind of highlighted from the image on the side. So you can see that with k-means, a lot of these objects, which will, to our kind of like naked eye, seem like they have distinct clusters, won't necessarily be seen with k-means. So depending on the type of data, it just may not be an effective algorithm to use. Now, when you're actually implementing clusters, it's important to know that often the final position that your clusters end up in are dependent on the way in which the initial clusters are randomized. So it's often recommended to run k-means a few times and then pick the best kind of iteration of the algorithm based off of the initial randomization. Another way to select a number of clusters is with the elbow method. And essentially what the elbow method is doing is you're looking for the within clusters sum of squares, which is the square distance between each point in the center. And what you're trying to do is find kind of an iteration at which you see the level of the WCSS kind of just begin to tail off. So as you can see on this example on the right, you can see within the first few number of clusters, there's a significant drop off. But then afterwards, you're not going to see much of improvement. The thing with k-means is that you'll always see an improvement with the amount of clusters you use, just because you're able to get more and more precise. However, having 100 clusters when you only have 120 data points isn't necessarily that effective, because then you're essentially just isolating each data point, and so the similarity will be very high, but it's not necessarily going to be as applicable. Another way to select the number of clusters is often when it's tailored to the application. So for example, if you're like an apparel company and you're trying to figure out the best size to assign to like small, medium, or large shirts, there you know that you have 3 distinct buckets that you're looking to classify. So then you could choose an optimal number of clusters as 3 because it relates to the application at hand. So some other applications that you'll see clustering used for is pre-processing. So when if you start to get into some more advanced pre-processing tools like PCA, you can use clustering to kind of help visualize and simplify your data. Other applications include compression of images to help reduce the number or the amount of data you have, or outlier detection. So for example, if you have a number of clusters and then see that there's a few instances that are significantly different than the majority of the clusters, you can then maybe look to see if it's an outlier and whether that's because of faulty data or if that's something that you're looking for within your specific application. So that's all for my presentation on unsupervised learning. Does anyone have any questions?
If you guys have questions, you can either unmute yourself, raise your hand, and I'll call on you, or you can send it in the chat. All right, if no one has any questions, thank you, Connor. That was really great. Really great to hear what you had to say. Is Andrew on the call?
Yeah, what's going on?
Hey, you ready to go? We can start early.
Ready to go, yeah. All right, is that visible?
Yep.
Sweet. Hold on here. All right, is that working?
Yeah, it's working.
Awesome, thank you. Okay, so hey, how's it going, everyone? I'm Andrew Simmons. I'm a project manager with QMind this year, and I'm gonna give you a quick intro to reinforcement learning. What we'll be covering today is just a general what is reinforcement learning, followed by some key terminology and concepts, and then we'll go over a few solution methods or approaches to classic problems. Then we'll go through a case study with the classic game Pong, and then I'll give you guys some resources at the end to learn a bit more. So first off, before we start with what's reinforcement learning, you might have heard today already, but machine learning is the study of computer algorithms that improve automatically through experience. So as you guys have seen throughout the day, there are three types. So there's supervised, unsupervised, and reinforcement learning. And so reinforcement learning is allowing the computer to learn what actions to take in certain situations to maximize a reward value. So we can start off with a kind of trivial example with Super Mario. So let's suppose that our reinforcement learning agent is learning to play Mario as an example. So the reinforcement learning process can be modeled through this iterative loop. So the RL agent, which is Mario, receives the state from the environment. And just to preface, I'll give all these definitions after, so just follow along. But so based on the state that Mario receives, he'll basically move right, for an example. So initially, all of the movements are random. And so now that the environment is in the new state from where Mario is now, it'll either receive a reward or no reward based on if either Mario moved in the right direction or if he's still alive. And so based on these events, it'll eventually learn what it is trying to do just from trial and error. And so the basic aim of the RL agent is to maximize the reward it can receive. Another example is very simple, and it's just with dog tricks. So imagine you're a dog and your owner is trying to teach you a new trick. They basically hold a treat in front of you and they're repeating some random word to you, but you can't understand it because you're a dog. So you just keep trying to do random actions until what you do lines up and you can receive that reward from your owner. And in the future, you'll know that if he tells you to sit and you do the correct action that corresponds to that random noise, then you'll be able to receive the reward. I'll go over some key terminology that I'd mentioned. So I'll give you guys a second to screenshot on the next slide if you want to keep the definitions, but I'll just verbally give them to you for now. So to start off, we have an agent. And so the agent is the thing that interacts with its environment and is trying to learn how to maximize a reward. So in the last example, it was Mario. The environment is what the agent's interacting with, and the environment determines what rewards the agent gets and the new state the agent then arrives at. And so the state is how the environment is at a particular time, and the state encodes all the information available to the agent. The action is a decision that the agent can choose to make, and the action is how the agent interacts with the environment. And at each state, there's a set of available actions that the agent can make. So in the Mario case, you could either jump, move left or right, or crouch, basically. And all these actions will correspond to a different reward signal. So the reward signal defines the goal of the reinforcement learning problem. And after each action is taken, the environment returns a number to the agent. The agent's only goal is to maximize the total reward it receives in the long run. So the next definition is value function, and this is the total amount of reward that the agent can expect to accumulate in the future when being in a particular state. So this function is a mapping from state to a real number. And so now we have policy, which is it defines the agent's decision making at a given time. So the policy can be seen as a mapping of the state of the environment to actions to be taken in those states. And so policies can either be stochastic, meaning that there's a probability that each action can be taken, or there can just be a binary yes or no, the action is going to be taken. And lastly, we have the model, which mimics the behavior of the environment and predicts how the environment will behave. And so if that was a lot of jargon and you want to actually read it or look at it later, you guys can take a quick snip of this. Sorry. And if not, I will continue with another example or some more information. So the next big topic is called reward maximization, which is kind of the goal of the agent in your RL problem. So the cumulative rewards at each step with respect to the action can be seen from this function. However, some rewards can vary based on certain situations. So for example, if a positive resulting move can be done with minimal risk to the end goal, then the next state will have a higher reward than that of a risky but more desirable move. And this is where a concept of discounting comes in. So for example, if in the Mario example, he moved right towards danger, then that might not be as good as jumping away from danger, even though they're both moves that will receive a reward. So discounting can also be seen through this problem here. So that is the equation factoring in discounting. So it can be seen as gamma represented between 0 and 1 as the discount rate. And so in this scenario, it's basically moves that prove to be riskier will have a higher discount and a smaller gamma or reward value. So in this example, if the mouse is to just gather the cheese around him, then that's much safer than going for the big payday in the top left corner while having to dodge shocks and cats on the way. So the next big term is a task in reinforcement learning. So a task is a single instance of a reinforcement learning problem, and it can either be continuous or episodic. So continuous tasks continue on forever until manually stopped by the user. And it basically chooses the best actions in real time while interacting with its environment. And so the main example of this is for automated day trading. So it will learn as it studies and make actions in real time with these stock trends. And the other type of task is an episodic task. And so there's a start and end point, which is called the terminal state. And so this creates an episode, which is a list of states, actions, and rewards. And the big example of this is playing Call of Duty or another shooter, where the terminal state is while you're alive, and you either shoot your opponents to get a reward or you get killed by them. And so another big term is exploration versus exploitation. So exploration is trying new actions that haven't been tried to explore what rewards are out there. And you may not be able to take advantage of the maximal rewards found, but you almost will always find the maximal rewards if it's an exploration heavy algorithm. And exploitation is kind of the opposite of that, which is choosing actions that are known to give high rewards because they have in the past without looking for anything that may be huge out there. And so there has to be a big trade-off with the algorithms you use between these two. And it's a unique problem to reinforcement learning. So the problem arises if you must maximize the reward through a limited number of actions, or if you want to receive large rewards as quickly as possible, or lastly, if you want your algorithm to converge to the optimal policy as quickly as possible. So it can be seen again through the mouse and cheese example, where we basically have a good amount of small cheese around us, but at the top of the maze, there's a huge sum. So if we only focus on the nearest reward, our mouse will never reach the big sum of cheese. It'll just exploit the small cheese around it. But if it does a bit of exploration, then it will be able to find the much larger payouts above. And so now we can go into two of the main approaches in reinforcement learning problems. So the first is a policy-based approach. And so we basically must optimize a policy which defines how the agent behaves. So the policy at a given state can either always return the same action, being deterministic, so like a binary thing, or it can have a distribution of probabilities of returning various actions. So it might want to move right in certain cases, but it could also have a probability of just moving a different way as well. And the other approach is value-based. So a value-based approach must optimize a value function, which is defined as a function which can tell us the maximum expected reward the agent will receive at each state. So the agent will use the formula below to decide which state to choose at each state, and will always take the one with the highest reward, adjusted with discounts, of course. So in this maze case here, you're obviously going to take the path that will maximize the reward and also get you to the end. So that will in turn get you to the end. So you can place rewards along the way that will then maximize this function and cause the agent to go the way you want. And so lastly, we'll look at a case study with Pong. So to solve the game, we need to feed the frames of the game to the reinforcement learning algorithm, which will then decide whether to move the paddle up or down. And so this approach can be considered policy-based, as we're continuously looking at random frames and producing random outputs, which will then be given a varying degree of reward, which will then feed the algorithm. And so in this case, the reward is basically the same as the scoreboard of the game. If the agent's score increases by 1, it knows that the moves it took in relation to the state of the game were desirable, and it's just a constant loop. So to train the agent to play the game, we feed in a ton of game frames, or can be considered states from the definitions, to our RL algorithm and let it decide which actions to take. And so initially the actions won't be anything but random, but the agent may be able to string together enough lucky moves to score a point. And when this happens, it receives a reward, which signals the agent that the actions it took were desirable. So in the future, the agent's likely to take these same actions in regards to the current state, and intuitively, the agent will learn to play the game. So there's a few limitations with this case in particular, with this type of algorithm. So during training, when an agent doesn't score a point, it lowers the likelihood that it'll take those actions with regards to the state. But the problem occurs if the agent was doing everything right until the very last move, then it wouldn't really make sense to discard all of the proper actions. But since we only can give rewards once the agent scores a point, there can be many complications with this approach, and sometimes the convergence will even fail. So there's a thing called rewards shaping that can help solve this problem, but it's a bit too complicated for just an intro, so it's a cool thing to look into afterwards. And so a couple of resources for you guys if you think reinforcement learning could be applicable to your QMind project, or you just want to get more info on it, is there's a sweet intro to RL course by David Silver, UCL, and DeepMind. So you can just Google it. There's a reinforcement learning textbook by Richard Sutton and Andrew Bardo, which I'm not positive how to get access to, but I'm sure Google might help. And then there's also a really fun website and library called OpenAI Gym. Some of the QMind founders started some of their projects on this. So the pendulum example is something that I remember seeing like 2 years ago, and it definitely piqued interest on the topic. So if you guys have any questions, feel free to let me know. If not, that's all from me.
Great, thanks, Andrew.